Okay, well, thank you. And thank you for the invitation to give a talk. And also, I really appreciate the organizer for putting this together. I do hope that our next meeting will be in person, but we'll see how it goes. So how much time do I have actually?
Well, you in principle have an hour and 10 minutes, but hopefully you'll leave 20 minutes of that also for discussion.
Sure.
Either.
Yeah. So yeah. I don't have many slides, so I can go slowly and then invite questions or comment during my talk too. So you're welcome to do that. I don't think I can check out the chat boxes. So probably just you can just shout your questions if you have any. Okay. So let me start. So the title of my talk is Narain to Narnia. And we have Narain in the title because this talk was inspired by very interesting two papers that appeared June of last year, about ensemble average of Narain conformal field theory. And Narnia will play some important role later in my talk. And when we realize that Narnia is an anagram of Narain, we cannot resist the temptation to use that as a title. So that's the title of my talk and also the title of the paper we posted, I think last month, and with Nathan Benjamin, Christoph Keller, and Ida Zeder. I think Ida and Nathan's are here, so they can correct me if I make any mistakes. So that's very reassuring. I'm not going to say who is going to be who. This was motivated, as I said, by a couple of a very interesting paper that appeared in June last year. So we have been very familiar with ADS-CFT correspondence for the last few decades. But just recently, a new type of holographic pair has been found in quantum gravity in lower dimensions, where quantum gravity theory is not dual to a single conformal field theory, but an ensemble average of conformal field theory in 1 or 2 dimensions. So this was first found in the context of 2-dimensional gravity. But then there are also some interesting examples in 3-dimensional gravity. And so this revived some decades-old question about the role of wormhole in quantum gravity, and also implication of its implication on holography. I hear some noise. Maybe if there is somebody who is not muting, probably it may be a good time to mute. Okay. So actually, we'll find some other, maybe possibly related, more technical puzzle in this context. So I would like to discuss that later in my talk. But what bothers us is that, so in the case of ADS-CFT correspondence, there are sort of a way of motivating or deriving it from consistency of string theory. So the way that originally Amarda Sena derived ADS-CFT correspondence is that, look, you have D-branes in string theory. And if you have lots of D-branes on the top of each other, then it behaves like black branes. So you have two ways of describing the same physics. One is in terms of open string ending on D-brane, and the other is in terms of general relativistic description of curved space near black branes. And so those two descriptions should be equivalent. And that leads to, but then Marusena realized that if you take appropriate limit of this equivalence, then you can extract some beautiful correspondence, ADS-CFT correspondence. So that's sort of physicist way of deriving ADS-CFT correspondence. We are very comfortable with that derivation. And of course, this has been confirmed by many examples. Compared to that, we do not have fundamental understanding of why ensemble average emerges. And so it'd be nice to understand it. And also, so one way of approaching it is to try to come up with more examples and see what are the patterns. So how this happens and when it happens? So far, all the examples are 1 and 2 dimensions. Does it happen in higher dimensions? So it turns out that there are variety of families of conformal field theory. We'll discuss several of them. And in some cases, we find that there is actually a reasonable gravity dual. And in some cases, there are puzzles. And in some cases, we'll find that there seems to be no holographic dual gravity series. And there seems to be some pattern for this. So we'll make some conjecture toward the end on when ensemble average have holographic dual gravity and when they do not. Okay, so that's sort of what I would like to talk about this morning, or this afternoon, or this evening, wherever you are. Okay, is that clear? Is there any questions so far? Okay, so let me move on. So let me first review what has been done. So there are 2 beautiful papers, one by Afghani, Jedi, and collaborators, and the other is Maroni and Witten, appeared back and back. So you start with Narain conformal field theory, which is a 2-dimensional free conformal field theory consisting of a scalar field. I assume there are C scalar field. I use C for the number of scalar field, is the central charge of this conformal field theory. And I assume that this scalar field takes value in the target space torus. So the target space is C-dimensional torus. And we know that toroidal compactification of string theory and conformal field theory are parameterized by Narain moduli space, which is this coset space, OC, C, divided by OC times OC, and also the discrete subgroup of OCC. So this is called Narain moduli space. It's a coset space. And basically this encodes the metric and B field antisymmetric 2 form on this torus, which is parameterized a marginal deformation of this 2-dimensional conformal field theory. So the partial function, so if you have, so basically the target space is flat, so scalar fields are free. So you have a partition function of C scalar field, which is given by Dedekind eta function. But since the target space is torus, so you have to sum over momentum and winding number. So that's given by this sum over this lattice. Okay. And well, actually this symbol is, yeah, that's good. Yeah, so the point, so let me explain the notation a little bit. So this is a Narain moduli space, but each point in the moduli space is actually lattice, because it's basically the coset space of this rotation in indefinite signature space, CC dimension. So you can think of this as a 2C dimensional lattice. And these lattices are actually lattice of momentum and winding number. Okay, so this is a formula. Okay, so these 2 people realize that you get something interesting by not considering single conformal field theory, but average of this partition function over this Narain moduli space. Okay, and this is the method for this had been developed decades ago by mathematician Ziegler, and he I think studied this in interesting number theory and the modular forms, and it turns out that you can beautifully average this over the Narain moduli space. And the other is given by sum of SL2Z over gamma. So you start with just the Dedekind eta function. So it's the same thing as the one that you have over here. But now you are summing this over SL2Z orbit. Here I'm summing over SL2Z over Z. So Z here is a T transformation of SL2Z. And the reason that I'm dividing this by Z is that the Z acts, this T acts trivially on the absolute value of Dedekind eta function. Because Dedekind eta function has inverse of Dedekind eta function has Q expansion, and these are all integer valued. There's a fractional power of Q in front, but if you take absolute value, it's invariant. So therefore, T part of SL2Z acts trivially on this partition function. So you just divide it by that, and then you sum over them. Okay, this is a mathematical fact. You can just derive this. And one nice way of deriving it, explained by the paper by Maroni and Witten, is to realize that this partial function satisfies differential equation. And differential equation has a form, the following form. So you have this, so this partial function depends on two sets of data. One is a moduli of the torus. Can you see the pointer, by the way? I hope you can see the pointer. And the other is a moduli of the target space. So it depends on both worldsheet moduli and target space moduli. Each of them has a Laplace operator because both has a metric. Moduli space of torus has a metric. This has a metric because this is a conformal field theory, so you have a Zamolodchikov metric. So with respect to that, you can consider Laplace operator. So it's actually very easy. So you have explicit form, so you can check directly by yourself that this partial function is an eigenstate of some of these two Laplace operators. So you add Laplace operator on torus moduli space to the Laplace operator of the target space, and it turns out that this is an eigenvector for this operator. And so then if you integrate this over Narain moduli space, then this eigen equation becomes just eigenvalue program for the Laplace operator on the torus moduli space. Because if you average this over moduli space, the Laplace operator is total derivative operator. So it's just integrate away with the appropriate boundary condition. And you can check that this satisfies the appropriate boundary condition because it is explicit form. So you can check that the boundary term disappears. So then you find that this, after integrating this over the Narain moduli space, you get an eigenvector of Laplace operator for torus moduli space. And then you have a unique answer to that. So that's a sort of, so this is a unique function which satisfies this eigenvalue program and has modular invariance, okay? So that's one way of deriving it. It's a very sort of explicit mathematical derivation. So now the question is physics. What's the physics of this equation? Well, so this right-hand side, so left-hand side is the ensemble average of Narain conformal field theory. Right-hand side is sum of SL to the orbit. So this thing is nothing but the partial function of C free field, 2C free field in target space. A natural thing to think about think about free field is in terms of Chern-Simon gauge theory. So abelian Chern-Simon gauge theory is dual to free scalar field in 2 dimensions. So it's natural to think it's a partial function of U1 to the C times U1 to the C Chern-Simon gauge theory in the bulk, okay? And you have twice as many U1 gauge field because so ADS-CFT correspondence said that each symmetry generator in the boundary CFT correspond to gauge symmetry in the bulk. In the conformal field theory, we have a C scalar field. So that means that C left chiral U1 generator and the right C right chiral U1 generator. So you have U1 to the C times U1 to the C gauge symmetry in the bulk. So that's what you get over here. So this is a natural thing. But then you have sum over SL to the orbit. So what does that mean? Well, what it means is that you not only have Chern-Simon theory for fixed solid torus in the bulk, but you have to sum over SL to the orbit. And so this was pointed out by Maroni and Witten 13 years ago, or 14 years ago, I think, that if you have a 2-dimensional torus, then you can ask what are the hyperbolic geometry bounded by this torus? And they show that it's basically all solid torus of a different way of filling in it. So if you have a torus where you can have various, you can choose cycles and you can decide which cycle is contractible in the solid torus. And you have different way of doing it. And that's actually parameterized by SL to Z over Z. So you can think of this as sum over solid torus, different way of filling solid torus, filling torus by 3-dimensional geometry. And in such a way that this 3-dimensional geometry has hyperbolic metric. Because so this was known to mathematicians, but actually Maroni Witten's paper gave nice pedagogical explanation of why it is that if you have a torus, the only three-dimensional geometry which has hyperbolic metric that bounded by that torus is the solid torus. And so right-hand side, you can say is sum over three-dimensional geometry bounded by the torus of modulus tau, which has hyperbolic metric in it. So you see that, so this suggests that the gravity dual of ensemble average of Narain conformal field theory is a Chern-Simons gauge theory, but not just Chern-Simons theory, but coupled to this funny two-dimensional topological gravity whose purpose of life is only to sum over possible hyperbolic geometries. Okay, no local degrees of freedom, just sum over hyperbolic geometry. So this very much like string worldsheet theory, right? So in string theory, you have conformal field theory in two-dimensional torus as a two-dimensional Riemann surface, but then there's also topological gravity coupled to it. And the purpose of topological gravity is to sum over a complex structure of the Riemann surface. So you integrate conformal field theory partial function over the moduli space of complex structure of Riemann surface. So that's two-dimensional gravity coupled to two-dimensional conformal field theory. So here we seem like we are seeing that bulk theory is a three-dimensional topological gravity. Sorry, three-dimensional topological quantum field theory, which is a Chern-Simons theory, coupled to topological gravity, which is summing over hyperbolic structure in the bulk. That seems to be an interpretation. That's what I wrote. So here, the outcome of this correspondence seems to say that if you average this torus conformal field theory over Narain moduli space, what you seem to get is a Chern-Simons theory coupled to topological gravity, which sums over hyperbolic geometry. Okay, so that's very interesting. So they did various checks. There are some puzzles about it. I will come back to that later. But for partial functions, there is a beautiful story. You can ask, how about correlation function? So as I tell you later, that in this case, there aren't interesting correlation function calculation you can do. So we'll discuss later other example for which we can also talk about correlation function. So, but this is just one example, one data point. So it'll be interesting to see whether there are other examples. So in this talk, I will examine three class of examples. One is orbifold conformal field theory, the orbifold of this theory. And also we'll discuss K3 and Calabi-Yau sigma models. So you can consider partial function of two-dimensional supersymmetric sigma model whose target space is K3 or Calabi-Yau. And you consider integrating over moduli space of K3 or Calabi-Yau and see what's get there. And we also discuss rational conformal field theory. So there are cases where actually there are several different distinct rational conformal field theory associated to given central charge. And I think this is actually related to the next talk by Jushi Duo. And so I look forward to the talk there too. So let me start with the Z2 orbifold of torus. So we are going to do obvious exercise, which is that you consider partial function of this Z2 orbifold and average that over the moduli space of Z2 orbifold. In the case of Z2 orbifold, the moduli space of this space is actually the same as original Narain moduli space because Z2 division does not freeze any of the moduli. So you just average over entire Narain moduli space again. And the partial functions can be calculated in this way. You have, so what you have is that you have original torus partial function, but you have to project that onto Z2 invariant state. And then you also have to sum over sum over twisted sector. So that gives rise to these terms. So now this is a first example. So we are going, this is very simple situation. And we can actually easily calculate the average. Because the only part that depends on Narain moduli space is this part, the same as the original torus partial function. So we already know the answer that these our friends did the calculation last June. And this part does not depend on moduli, so it just comes out like that. Okay. So therefore, this is the answer. So we can within a few seconds we can derive the ensemble average. The question is that, so does this have an interpretation as yet another bulk gravity theory So what kind of bulk gravity theory you get? Well, the obvious guesses are following. So what Z2 orbifold means that you are gauging Z2 symmetry on the boundary conformal field theory. Okay, on the boundary conformal field theory, there is a Z2 symmetry, which is to flip the sign of all the scalar field at the same time. But ADS CFT correspondence says that the derivative of this scalar field, the U1 current associated to this scalar field, should be identified as a boundary value of the bulk gauge field. So if you are going to gauge the boundary Z2 symmetry to flip the sign of scalar field, you should also identify the bulk gauge field by this Z2 symmetry. Now, so I wrote this paper with Daniel Harrow a few years ago saying that in ADS CFT correspondence, there is no global symmetry in the bulk gravity theory. But that we assume that the bulk gravity theory has Einstein gravity coupled to finite number matter field, and bulk gravity theory has black hole. And in fact, the black hole is very important for the absence of global symmetry. So this theory doesn't have Einstein gravity, and this theory doesn't have a black hole solution. So it seems like this theory can have global symmetry. And in fact, Chan-Simon theory has Z2 global symmetry. So the reasonable conjecture is that Z2 orbifold, ensemble average of Z2 orbifold is equivalent, the holographic dual, to Chan-Simon theory coupled to topological gravity with Z2 symmetry gauged. Okay, so that's a tentative expectation. And then you can ask, where does that borne out? So one can try, for example, consider Chan-Simon partition function, but project to the Z2 invariant state because we are gauging Z2 symmetry. But this does not work. You can easily check that the ensemble average of this is not the sum of these things. In fact, the ensemble average is this. So you are missing some part of this by just doing this calculation. But in fact, you can rescue this for the following reason. So we are gauging this Z2 global symmetry in the bulk. So now there is a distinction between global symmetry and gauge symmetry, of course. But that distinction exists also in discrete symmetry. So in discrete symmetry, one way to distinguish whether discrete group is acting as global symmetry or gauge symmetry is that in the case of gauge symmetry, we'll have vortices. So here is an example of vortex. So the red curve is a vortex. So you can have a vortex going around the bulk. And what happens is that as you, so this vortex is a codimension 1 object, sorry, codimension 2 object in the bulk. And if you go around the vortex, then you have a non-trivial action of discrete group symmetry. So for each discrete group, you can consider a vortex, which is where as you go around the vortex, you have an action of the discrete gauge group symmetry. Okay, so you can have this vortex going around, and you can ask, well, what is the partition function of the theory if you have a vortex in it? And you can actually calculate this, and you find that these give rise to additional contribution. And vortex can be in the various different configurations, so you have to sum over them. And then if you sum over them, voila, you get the right answer. So this is very happy situation. So you can actually explain this as saying that now we have a duality between Z2 orbifold theory on the boundary, and then bulk theory, which is a Chan-Simon theory, with the Z2 gauging coupled to topological gravity. Okay, so this works out very well. There is another perspective of this result, which will be useful later, which is the following. So this conformal field theory is rational in the sense that, well, not quite rational, but you have many chiral symmetry. The big chiral symmetry, you have a U1 to the C chiral algebra, current algebra, but you have to divide by Z2. And so you have this chiral symmetry, and you can decompose this partition function in terms of representation of this chiral symmetry. So if you look at the representation of this chiral symmetry, you find that there is a vacuum representation, and there are three inequivalent special representation which are independent of the moduli. But then there is actually a continuous family of representation parameterized by the conformal weight of the theory of the representation at the highest weight. I'm sorry, highest weight state. And then you can sum, and then this part depends on the Narain moduli. Okay, so you can see that the average of this partial function Narain moduli space is actually equal to just sum of SL to the orbit of these moduli independent part. So this seems to be another way of looking at it. This is true in this conformal field theory, OP4 theory, and original Narain ensemble average of Narain conformal field theory too. This result generalized to other OP4. And these cases are more interesting, and calculations are a little bit more non-trivial. The non-triviality has to do with the fact that here we could just borrow the calculation by our friend from last June. Because Z2 OP4, Z2 gauging does not freeze any of the Narain moduli space. So therefore, you can average over the entire Narain moduli space. But if you consider Z3, Z4, Z6 OP4, then actually these freezes complex moduli. In order for the torus to have these Z3, Z4, Z6 gauge discrete symmetry, the complex structure has to be of the particular form. So that means that we cannot average over complex structure moduli. We only can average over scalar moduli. And so we have to do new calculation. So it's good, it's fun. And we did that, and the result agree. So namely, the answer is that if you average ZP OP4 the partial function, then you again get the expected answer, which is first part is a partial function of the Chern-Simons theory with ZP projection. But also you have to sum over configuration of ZP vortices in the bulk. And there are various configurations, you have to sum them up. And then these two results agrees. Okay, so that's a happy situation. So how about correlation function? So we have so far talked about the partial function. Well, so you'd expect that ensemble average of any observable conformal field theory should have a nice bulk dual meaning. And so you can ask, how about correlation function? Well, it turns out that in the original example of Narain conformal field theory that people studied in June last year, there is actually no interesting correspondence in correlation function. Because, well, so what kind of primary field do you have in the torus conformal field theory? Well, you have identity and you have winding state and momentum state. But winding state and momentum state are funny because the conformal dimension of this depends on moduli. So therefore, when you try to average, the conformal dimension changes. But more seriously, what this theory does not, we don't expect bulk dual of these operators for the following reason that you have U1 to the C times U1 to the C symmetry. Somebody has to mute the microphone because we can hear what's going on in their room. Let's see, let me continue. So these are, so you have U1 to the C times U1 to the C symmetry. And if you have winding and momentum state, these are charged with respect to this symmetry. Okay? But in the bulk, you don't have any charged state. What you have in the bulk is the Chern-Simons theory coupled to topological gravity. And Chern-Simons theory has no charged particle in it. So you don't have bulk dual of this. But you can ask, well, how about Wilson lines? Well, Wilson lines are not particle, but you can start from Wilson line ending on particular point and going to the other point. And you can ask, well, can you use that as a sort of bulk dual of correlation function? Well, you can we didn't believe that was the case, but we tested it. We actually calculate. You can calculate the Wilson line expectation value, and you can compare that in the bulk, and you can compare that with ensemble average of correlation function of winding and momentum operators, and you can show explicitly that they do not correspond. They are not the same. So as expected, because you don't have charged particle in the bulk. So for all these reasons, there is no interesting correspondence for correlation function in this case. But for orbifold, you have interesting correspondence for the following reasons. In addition to winding and momentum state, you have twist state, which is that you have operators on the conformal field theory, and you go around that operator. So the operator in conformal field theory, if you insert it, it's in codimension 2 singularity. And so therefore you can go around, and then you can have action of a discrete group which you are gauging. And in conformal field theory, it is well known that, so these are called twist operators. And each twist operator corresponds to fixed point of this action. So in Z2 case, there are for each, so torus has C direction. And for each direction, you have 2 fixed points. So suppose, for example, you have S1 of circumference 1. Then 0, the origin is a fixed. If you flip the coordinate x to minus x, the x equals 0 is a fixed point, but x equals half is a fixed point because Z2 action of 1/2 is minus 1/2, which is the same as 1/2 because we are periodically identifying the space by 1, shift by 1. So therefore, for each direction, you have 2 fixed points. So you have 2 to the C fixed point. So I parameterize that by some vector, a C-dimensional vector epsilon, taking value in 0 or her. And then you can consider correlation function. Say, for example, here 4-point amplitude. If you open the classic paper on orbifold in the 80s, you see that you see how they explain how you calculate these things. And the first thing is that there is a charge conservation. So some of these vector has to sum up to be equal to 0, mod Z2. And then, but if you add, so you can average this. I'll tell you how you can calculate it, but you can average this, and you find that actually, in order for the answer to be non-zero, in addition to these conditions, these epsilon has to be pairwisely the same. So namely, epsilon 1 has to be either equal to epsilon 2, or epsilon 3, or epsilon 4. Okay. So let's, for simplicity, consider simplest case. Epsilon 1 is one case, particular case. Epsilon 1 is epsilon 2, epsilon 3 is epsilon 4, but other cases can be considered in similar way. Okay, so so correlation function of twist operator in the 80s, people studied how to calculate it. The idea is the following. So suppose you have a sphere, and suppose you have a Z2 conformal field theory on the 2-dimensional sphere, and you have twist operator at 4 points. As you go around each of these 4 points, you have an action of Z2 action, you get -1 acting on each scalar field. The way you calculate it is to consider universal covering of this Z2 action. So what you do is that you put branch cut between these, the pair of this twist operator. As you go around it, you go to different Riemann surface, 2-dimensional, in this case, 2-dimensional sphere, and come out from this branch cut. And as you go around it, you come back to the original. So you have 2 spheres with 2 branch cuts for each of them, and they are glued together. And what you get is a 2-dimensional torus. So the universal covering of a 2-dimensional sphere with 4 Z2 branch cut is a 2-dimensional torus. So basically, you calculate the partial function of that torus, and that gives you this correlation function. So you can see that this is actually the same as torus partial function. There are some constraints on the winding number and momentum. So it's slightly different from this kind of things, but it's very similar to this. And so therefore, you can calculate the ensemble average by using very similar technique. So that's what we did. Okay. So this can be this has a form of the partial function on the 2-dimensional torus because it is a branch cover, Z2 branch cover of a 4 point on the sphere. And we can average it in a similar technique. because there is some constraint on momentum and winding number going through the branch cuts, so you don't get the sum over SL to Z, but you get sum over gamma 2, which is a congruent subgroup of SL to Z, where off-diagonal components are even integer and diagonal components are odd integer. That's what Z2 means. Okay, so you get a slightly different non-holomorphic modular function in this way. So here you have a correlation function depends on the anharmonic ratios of the 4-point, that is X. And here the answer depends on tau. The relation is obvious, right? So you have a sphere with 4-point, branch point, so the twist operator on 4-point. And X is an anharmonic ratio of these 4 points. But I told you that if you consider universal covering, the covering of this Z2 branch, then you get the torus. So tau is a moduli of the torus. Okay, there is an explicit relation between these two that's given by this formula. So namely, so if you have a harmonic ratio X of the 4-point over which you have Z2 branching, then the corresponding torus tau is given by the ratio of hypergeometric function, the classic mathematics. So those are the kind of things that Abel and Jacobi worked on in the 19th century. And the inverse of this is given by what's called lambda function, which is given by fourth power of the ratio of theta function, elliptic theta function. Okay, so anyway, so with this, the average ensemble average of correlation function twist operator is given by a gamma 2 orbit of this Paschen function looking thing. So you can ask, well, what is the physics? So this is a mathematics. This you can calculate the same way that our friends calculated the average of torus Paschen function last June. But question is that how do you interpret it? Actually I'll tell you that there is a beautiful geometric and physical interpretation of this summation, which has to do with the notion of rational tangles that I will explain later. But let me first give a few observations. So I told you that there is a relation between this anharmonic ratio X and the torus moduli tau given by this formula. Okay? So those are the things that I teach for undergraduate students in my course in mathematical method in physics. And one of the beautiful things that I teach in this kind of course is that a hypergeometric function has a monodromy property. That as X goes around 0, 1, and infinity, then you get the linear combination of hypergeometric function corresponding to the same hypergeometric differential equations. So that generates some transformation tau. And that transformation is actually gamma 2. So there is actually a relation between gamma 2 and the monodromy of a sphere with 3 points. Okay. And the identification is very easy to establish because both of them are free groups. So if you generate, there is a correspondence between generators, then that's it. So you can actually check it directly. But what monodromy has to do, well, with this kind of interpretation. So that's where the rational tangles come in. So let me introduce a notion of rational tangle. So I told you that if you have, so this is two-dimensional sphere. So suppose it is bounding some hyperbolic geometry, okay? So of course, I mean, the natural thing to consider is the three-dimensional Poincare space, that hyperbolic space. And so you have a Z2 twist operator at this 4 point with X being a harmonic ratio. As you go around each of these points, then you get Z2 action. So if you think about it, and if you remember my definition of Z2 vortex that I told you earlier in the bulk, so this is a definition of Z2 vortex, then you see that these are natural endpoints of this Z2 vortex in the bulk. So you can expect that these twist operator, each of these twist operator must be endpoint of Z2 vortex in the bulk. So you have Z2 vortex emanating from these things, right? And so I actually color-coded these Z2 vortex because there are actually lots of choices of twist operator parameterized by this vector epsilon. So you would expect that there are correspondingly the vortex or should also be colored. So, and then I told you that the average ensemble average forces pairwise identification of these twist point, fixed point. So that means that there must be two different kind of vortices. So natural thing is to connect them. So you can connect these. So this is a natural configuration of Z2 vortex you can expect in the back. So now what is the monodromy do? Well, if you act SL, so what we wanted to do is to understand what this Z2 action means. So the gamma 2 action means. But gamma 2 action is a monodromy transformation for X. So that means that if you start with this configuration of Z2 vortex and act monodromy of X around 0, 1, then in the bulk you would get gamma 2 transformation. So if we want to, so we want to understand what gamma 2 transformation in bulk is doing. It is doing monodromy transformation on the boundary. So this generates some kind of complicated topological configuration of these vortices. And these configurations are called rational tangle. So this notion was introduced by John Conway in 1967. And he introduced this notion because he wanted to classify knot. And he wanted to decompose knot in 3 dimensions in the simplest component. And these are rational tangles. So rational tangle is a following concept that you start from this trivial tangle. Tangles are this arc in the 3-dimensional space ending on the boundary. And this is a sort of trivial tangle. They are not tangled at all like this. And then he considered rational tangles, which are basically generated by acting monodromy transformation on the endpoint of these tangles. There is actually a beautiful theory of tangles. So for example, each tangle corresponds to a continued fraction. And so if you give me continued fraction, I can give you corresponding rational tangles. And you can use this continued fraction to do lots of interesting things. Conway has demonstration of some tangle dance of a graduate student during his talk in one of his videos, for example. So it's lots of interesting things to watch. So what we learned is that you can think of this. So we are trying to understand what the right-hand side means. So right-hand side can be interpreted as configuration of Z2 vortex in the form of rational tangles. Okay, so that's nice because it's natural that since we are considering Z2 vortex ending on the boundary, we should consider all possible configuration of tangles. But then this poses a puzzle. So why only rational tangles? In fact, you can easily come up with a configuration of Z2 vortex, which is not rational tangle. So here, this is a rational tangle that as X goes around 1, you generate this configuration. But you can easily show that by having X going around 0, 1, and infinity, you can never create a configuration like that. So these are called irrational tangle or non-rational tangles. So you can, the question you might ask is that when you do the ensemble average of the 4-point amplitude, the bulk dual has a configuration of Z2 vortex. Why we consider this kind of configuration? We don't consider this kind of configuration. Okay? So that's a puzzle. So we are stuck with this puzzle for a few months until we stumbled upon the beautiful video by William Thurston called Tangle to Not to Narnia. And so I would like to show you this video. It's a delightful video for 9 minutes. I'm not going to show the entire 9 minutes. I'm going to show you the first 3 minutes of the video where he introduced a notion of branch covering over knot in 3 dimensions. So you consider knot in 3 dimensions, and you can consider branch cover over this knot, and that generates different 3-dimensional geometry. Okay, so let me show you the first 3 minutes of the video. Can you see Thurston?
Yes.
Good. So let me make sure. So if you cannot hear him, let me know.
I want to take you through a little
Can you hear him?
exercise of the imagination
Yes.
that will help understand and distinguish.
Did you hear him?
Yes, but can you crank up the volume a bit?
Okay,
I
sure.
want to take you through a little exercise.
Sorry. So let me crank up the volume a little bit. Okay, so let me start. And if it is still too low, let me know, okay?
I want to take you through a little exercise of the imagination that will help understand and distinguish different kinds of knots. So we're going to begin with the most ordinary knot of all, the unknot. Here's a unknot in the form of a loop of tubing. But what you may not realize right away is that this tubing has magical properties. It creates a singularity in the fabric of the universe. And what it does is that if you look through the tubing, the universe you see through the tubing gradually drifts away from the universe on this side of the tubing. And over many years, its properties and its occupants change a lot. That world through the tubing is called Narnia. I can step through this magical loop. This is like a doorway into another world, the world Narnia. Here we are in Narnia. We've been exploring, we've had lots of adventures and seen many unusual and interesting sights, but we've arrived finally back at this coil, this unknotted coil. And when we look through it again, we see Earth. I'm kind of tired of being in Narnia, so I'm going to step through the coil and I'm back in Earth again. This tubing creates a two-way branching in the universe. When I go through it once, I go from Earth to Narnia. If I go through it again, I go from Narnia back to Earth. I can keep going as many times as I want, from Earth to Narnia. And it doesn't matter which direction I go through. I went from Earth to Narnia. Here I'm in Narnia, and I can step back out, and I'm in Earth again, and so forth. This is the property of the tubing. But the tubing doesn't have to be just arranged as an ordinary kind of unknotted door. What happens if you knot the tubing? Will it create the same kind of split in the universe, or will it create a different kind of split? Well, let's try and find out.
Okay, so I'm not going to show you the entire 9 minutes of video. So what Thurston is going to do, and actually it's very interesting. So I recommend you to watch it at your leisure. So he's going to explain now what's going to happen if you consider a double branched cover over trefoil. Okay, so that's what he's going to tell you, and you'll find out. But so you can see the point I wanted to make is that for each configuration of this Z2 vortex, you can consider a double branch cover of this vortex, and it generates new geometry. Okay, so that was, and then he explained that for unknot, and he's going to explain, if you watch the rest of 6 minutes, how you do the calculation for trefoil. So you can ask a same question for tangles. So suppose you are given tangle, then you can consider double branch cover over this tangles, Z2 vortex. Then what you have is that you'll get some three-dimensional geometry bounded by three-dimensional sphere with double branch cover over the boundary. But then the bulk is also double branch cover over this rational tangle. And what is that geometry for the bulk? Okay. Well, then you can ask, well, does that kind of construction make any distinction between rational tangle and non-rational tangle? So there is actually a beautiful result by Hodgson and Rubinstein in 1985. A mathematics friend told me this was a very important paper about knot theory. And one of the corollary lemmas that they prove in this paper says that if you have two tangles, like two tangles ending on the sphere, and if you consider double branch cover of the tangle, then it is a solid torus if and only if the tangle is rational. You see, we are considering double branch cover over 4 points on the boundary. on the boundary, double branch cover, we are considering 4 twist operator on the boundary. So if you consider double branch cover on the boundary, you get a torus. So in the Baruch, you should get some geometry which is bounded by torus. And those people proved that this Baruch geometry is a solid torus if and only if the Tangle configuration is rational. Okay, but Maroni and Witten showed that it is only the solid torus which has hyperbolic metric. So therefore, what you can say is that solid torus is the only 3-dimensional geometry with genus 1 boundary that allows a hyperbolic metric. So this is a very satisfying answer. That is that we are supposed to be summing over gamma 2, not SL2Z, but gamma 2. And this can be understood as sum over configuration of Z2 vortex whose double branch cover allows hyperbolic metric. So again, the Baruch gravity is coupled to Z2 gauging of Chern-Simons theory. Coupled to the Baruch theory is U1 to the C times U1 to the C Chern-Simons theory divided by Z2 gauge group, coupled to topological gravity, whose purpose of life is to sum over hyperbolic geometry. This generalizes to the P orbifold. And so I guess I'm running out of time a little bit, so I should speed up. But here again, you can do the same story, and then you can actually prove that you can actually, there is a mathematical result that says that now we have to consider P-fold branch cover. And there's a beautiful mathematical result which says that this is the P-fold branch cover over 2 tangle is a genus P minus 1 handle body if and only if the tangle is rational. So again, there is a particularly, there is a special thing about rational tangle in this case. Apparently this theorem is even, this lemma is even deeper one. This follows from Smith's conjecture about knot in 3 dimensions, which is one of the deepest result in the knot theory, I'm told. Okay, so now I want to tell you a little bit about the puzzle we are still having about non-factorizable amplitude. So I told you that one of the motivation for one of the reasons this is interesting is that this revives the question about the role of wormhole in quantum gravity and its implication in holography. So for example, so this dates back to Coleman, but Mardasena and Maotsu pointed out that there is some puzzle if you consider wormhole configuration in the context of ADS-CFT correspondence, because it gives rise to ensemble average of that kind, and that's what we are seeing. So in particular, that means that if you consider product of partition function and average them, then you get a result which does not factorize, and you can imagine that you can interpret it in terms of wormhole connecting these 2 geometries. So the puzzle we have right now is that we don't have a yet coherent picture of what kind of Baruch geometry we are supposed to be summing when you have a product of partition function or product of correlation functions. So in those cases, what you have is that you have 3-dimensional geometry, which is bounded not by single boundary, but multiple boundaries. So you can certainly consider 3-dimensional geometry, which are various different boundary components to it, but there are actually constraints to it. So for example, Maroni and Witten and in June last year calculated, for example, the torus partition function and considered product of torus partition function and average. And since torus partition function depends on moduli, so the product of ensemble average is not the same as average, So the ensemble average of the product is not the same as product of ensemble averages, right? Because the average of product is not the same as product of average. So that means that there is a non-factorizable contribution to product of correlation function. So that means that you must have Baruch geometry which have multiple boundary component to it. In the case of a torus partition function, would you have a three-dimensional geometry bounded by two component of two-dimensional torus? Okay. So certainly you can imagine configuration like that. You can consider solid torus, and you can remove smaller solid torus from the middle. So here you go. You have a three-dimensional geometry bounded by two boundary components. So Maroni and Witten says that, well, that seems to be a good candidate for bulk geometry. But it turns out that there is a mathematical fact that even though you have topologically such a configuration, but you cannot put the hyperbolic metric on it. So you can put the hyperbolic metric on the solid torus bounded by one boundary torus. But in the case of ADS correspondence, the distance to the boundary has to be infinite. You can remove solid torus from the middle, and you have a hyperbolic metric to it, but the distance to the inner torus is finite. So that seems to be not the configuration you would normally consider in the ADS-CFT correspondence. And you can actually prove that you cannot have a three-dimensional geometry with two boundary torus components for which the distance to each of the boundary torus is infinite. So that raises the question of whether we should sum over these configurations or not. And we have some kind of opposite of the puzzle in the case of orbifold, in which case you do, so assuming such configuration is, so because the torus partition function is not factorizable, that is that if you take product of torus partition function and average, that is not the same as product of ensemble average of each of the torus partition function. So you can ask, well, what about the contribution from twisted sector if you consider torus orbifold? In that case, you can consider similar configuration. But so I don't have time. So if there is a question, I can discuss it. But it turns out that those should not contribute from the CFT calculation. So that's a puzzle. We also have a similar puzzle for the sphere correlation function. And again, there is a puzzle about the relation between product of ensemble average and average of the product. There seems to give rise to different answer. So this has to do with the question of what kind of geometry, wormhole type geometry that we should allow, we should count, and what kind we should not allow. There seems to be we do not have yet completely coherent picture. So actually, just this week I was talking to my collaborator, and we realized that this second puzzle may have a solution, but we are still working on it. So we are still sort of confused about the situation. Okay, so in the remaining 5 minutes or so, let me tell you a little bit about other example. So you can ask, what about K3 or Calabi-Yau sigma model? So we tried this, and then we found that there seems to be an obstruction, that there seems to be no reasonable bulk dual of ensemble average of K3 or Calabi-Yau sigma model, for reasons very similar to the observation that there seems to be no consistent pure gravity theory in 3 dimensions. So this is an ongoing puzzle. So people asked, would there be a consistent quantum gravity which consists only of graviton? In the case of 3 dimensions, that means boundary graviton corresponding to Virasoro algebra, and nothing else until you get to the BTZ black hole. Okay? So namely, that would be the natural thing you would expect if you quantize Einstein gravity in the bulk. You can ask, well, is there a natural consistent conformal field theory to it? So this question was posed by Maroni and Witten, I think, and they discussed that. And more recently, lots of people worked on it, and myself with Nathan Benjamin, Sophie Xiao, and Yifan Wang also wrote some paper a couple of years ago, pointed out that there is an issue with this, that if you try to find bulk conformal field theory dual for pure gravity, you inevitably get some kind of a negative norm state. Okay? And it seems like you have a similar program for this correspondence if you try to force the correspondence for K3 or Calabi-Yau sigma model. So various attempts failed. So this led us to expect that there is no reasonable bulk dual of ensemble average of K3 on Calabi-Yau. In view of time, I will not elaborate more on that. So this is related to the next talk by Jushi Luo, probably, that we can also ask whether there is a bulk dual of ensemble average of rational conformal field. What does that average of rational CFT mean? Rational CFT is an isolated one thing, right? But here is what we mean. So consider minimal model of conformal field theory, the minimal Virasoro conformal field theory, whose central charge is given by this famous sequence. We're considering unitary conformal field theory. So in fact, for m greater than or equal to 5, there are actually 2 or 3 inequivalent conformal field theory with the same central charge. And because there are various different ways of constructing modular invariant partial function out of representations of conformal field theory, Virasoro algebra with this central charge. So you can ask, well, suppose you sum over orbit of SL to the orbit of the vacuum character, can you interpret it as sum of conformal field theory with non-negative weight? Well, you can show that it works all the way from 5 to 13. So this is interesting. M equal 5, it works. M equal 6, it works. 7, 8, 9, 10. And being physicist, you might imagine that it's going to be true for all m. And it fails at m equal 14. And the fail, in a way that you can find that you can, if you calculate this, then you can write it as sum of a partial function of different conformal field theory, but some of the coefficients are negative. Okay. So that seems to be a problem. But on the other hand, it seems like there are infinite sequence of cases that works. And similar observation was made by Sunil Mukhi and collaborators for the West-Zumino-Witten model too. So again, in that case, it is parameterized by K, the level of SU2 current algebra. And they found infinite sequence of K for which there is an interpretation like that. So that's very interesting. So what we learned from this? Well, so we looked at 3 different examples. The orbifold conformal field theory, K3 and Calabiao sigma model, and rational conformal field theory. So what kind of lesson? So we came up with one general pattern, which is the following. So suppose we consider conformal field theory, family of conformal field theory, and consider ensemble average of its observable, like partial function or correlation function. They seem to have holographic interpretation when the central charge of the conformal field theory is equal to the critical central charge. So critical central charge is the following concept. You consider vacuum representation, and then you consider asymptotically large energy state for the vacuum representation. It has Cardi behavior, but it has Cardi behavior with effective central charge given by C critical. So that's the definition of critical central charge. Okay, you can think of this as basically the estimating the number of symmetry generator of conformal field theory, because state in the vacuum representations are all chiral operators. So they are all symmetries in some sense of conformal field theory. So critical central charge measures how big the symmetry is. Okay, the actual central charge is at least as big as critical central charge, but sometimes larger. So what you can see is that in the case of Narain conformal field theory of orbifold conformal field theory, critical central charge is C, the same as the actual conformal field central charge. But for Calabiao or K3 sigma model, C critical is smaller than the actual central charge. The actual central charge is equal to 3/2 of the complex dimension of the target space. And but the critical central charge is 3. So therefore, for K3 or higher dimensional Calabiao manifold, the C is actually bigger than a C critical. For rational conformal field theory, in certain definition, C is equal to C critical. So it's reasonable to think that this is a necessary condition because it sometimes works, sometimes don't work. So anyway, so this seems to suggest that this type of correspondence works when you have sufficiently large symmetry. So maybe that's why we don't see something like that in higher dimension, because it is only in 2-dimensional or lower where conformal field theory has large enough symmetry so that you can organize most of the spectrum in terms of symmetry. So that may be the lesson for higher dimensional conformal field theory. But we need to understand a bit more in order to make a definite statement. So that's all I wanted to say. Thank you for your attention. Thank you.
Thank you, Hiroshi. That was beautiful work and beautifully described. So let's all thank Hiroshi with our, either by unmuting and clapping for real or putting up your little clap symbol, however you want to do it.
Thank you.
So there's plenty of time for questions. And I think rather than me scanning a million boxes for little hands raised, I'm just going to try and do it by having you unmute yourself and asking the question, see if that works.
I have a question.
Yes, please.
Hello, Hiroshi.
Hi, nice to meet you after a long
nice
time.
to see you. Yeah. So yeah, I have a question about your ensemble average for rational conformal field theory. You know, for the minimum model, there's no moduli. So I don't understand what you mean by averaging in that case.
So what I mean is that for m greater than 3, you have the moduli space is set of points consisting of 2 or 3 points.
Yeah.
So it's a very simple moduli space. So I regard these as a moduli space.
I see.
Yeah, that's what I mean.
Just averaging over those fine number of equivalent CFT, you know, with different partitions.
Yeah, I thought that was what the ensemble average means, that when you have continuous family, you integrate them. When you have discrete set, you sum them.
Okay, I see. Another thing I have to admit I don't know is, what do you mean by critical central charge? Because I know what the central charge is. But
So this is the definition. So, so you know that the central charge appears in the commutator of Virasoro algebra.
Yeah.
There is a famous work by John Cardy that says that if you have a central charge of the Virasoro symmetry, and if you have conformal field theory for which this is a symmetry, then you can estimate the asymptotic density of state for large conformal dimensions.
Right.
So the partition function is modular invariant. So you can use modular invariance to estimate how many states you have for large conformal dimensions. So in general, yeah, you see what I mean?
Okay, so but let me ask you.
So that's the definition of central charge, and critical central charge is defined by restricting that to the vacuum representation.
Okay, so let me see if I understand this correctly. For rational CFT, which I'm familiar with, the asymptotic density of the state is determined by this S transformation, right?
So, yeah, so it's given by this.
That case, so in the rational case, is the is central charge always the same as the critical central charge?
Yes.
I see. So that's why So, but
the reason for this is very simple. The reason is very simple. So in rational CFT, there are only finite number of irreducible representation of Virasoro algebra. That's why it's called rational. So that means that so that means that the asymptotic density of the whole partition function has to be the same as the asymptotic density of the vacuum representation. But the only way that they are different is that there are when you have infinitely many representations. Because if you have a finite number of representations, all scales in the same way.
I see. Okay.
So therefore, it's inevitable that rational CFT, C is equal to C critical.
Okay. All right. Great. Thank you very much.
In the case of orbifold conformal field theory or torus conformal field theory, I think the reason C is equal to C critical is that the rational points are dense. So that raises the question of whether rational points are dense for K3 or Calabi-Yau sigma model. But yeah.
I see. Okay. Great. Thank you very much.
Question?
Yes, sir, Isaac.
Hi, Hiroshi. Nice to see you. And
I like your background. You are in an impressive location.
Well, it's Yale Library. I used to go there when I was.
Yeah, you are alumni from there.
Yeah, alumni and faculty member. I used to be. So I used to go there quite a lot. So anyway, Very nice talk, very interesting results. I'm learning for the first time, so excellent. So one question, just for clarification, about the your comment about the SU2 sub K WZW.
Oh yeah, so this is not my result. This is by Sneer and friends.
Right. Can you clarify what the comment is about that?
Oh yeah, so the comment is the following. So so SU2 based Witten model, for each K, you have a conformal field theory, but sometimes you have several inequivalent conformal field theory because you have a different way of constructing modular invariant partition function out of SU2 affine Lie algebras, right? So so the question is the following. So you have a vacuum representation of SU2 Witten model, and you do sum over this gamma in the same way. You can actually show that you can always write it in terms of sum over partition function, different inequivalent partition function of this modular invariant combination of SU2 affine Lie algebra. The fact that you can always do that is obvious mathematical statement coming from modular invariance, etc. But the question is that are all the coefficients non-negative? And it happens sometimes, it doesn't happen sometimes. But these people show that in fact there are infinite sequence of cases where it happens. That's a state.
Okay.
Yeah.
Thanks.
Another question?
Yes.
I was asking, are there any other questions?
That was a meta question, yes.
I think part of the reason for the absence of questions is the clarity of your presentation, I should say. I think Nick has.
Just more broadly, if you could imagine if you had, say, some product of CFTs that you could average over the moduli of one of the factors and do things like this, where you don't average over every modulus, but you average over some sector of the theory. Is that something you could do, and is that something that could be useful and meaningful in this context?
That's a very interesting question. So for example, why do you think that you only average on the sector, or are you saying that?
Well, it's more a mathematical question, but I could imagine, for example, a system where you could think of the averaging as like coarse graining over a sector of the theory, where you say these are details I don't care about, but there are certain observables that I do care about. And so I could actually ask about correlation functions in, say, some C equals 1 theory. It was interacting with the bath of C equals 27 theories, and I can average over the big theory and look at how it might give me interesting correlations in the smaller theory. So rather than just, you've averaged over in some sense everything, and descended to a topological theory, but maybe there's a halfway house where you can descend to some much simpler theory from a much more complicated theory by averaging over a more complicated subsector.
Yeah, so actually, I have some issue with that, because if you have, for example, suppose you don't do ensemble average, then there is a problem with considering Barak dual or product of conformal field theory, as you know, because then it means that you'll get two gravitons. Yeah. Because each conformal field theory has gravitons, and each has energy momentum tensor, so you have a dual of that. So you get two gravitons. That's not consistent Barak theory.
No, I think probably what I really thinking of is maybe you've got some, I'm sort of thinking more along the lines of quotient CFT. So I've got one CFT, but inside that CFT, I've got some sub-CFT I'm particularly interested in, or some way that there's a super selection sector that I can say, I'm interested in the field theory made by this sub-algebra of the chiral algebra. And I want to average over everything else.
But you have to somehow cut it out in such a way that you only have one energy momentum tensor. So it cannot be just totally decoupled subsector somehow.
Yeah, no, that would be boring. If it was totally decoupled, then you just get the CFT. You can't, I'm trying to think of sort of some kind of analog of the quotienting model. You see, in some sense, what you've got here is a really cool reduction of a complicated CFT to something essentially a topological field theory. And I was just wondering whether there was some way of doing some kind of quotienting where you have a very simple dynamical theory that emerges from averaging over a much more complicated one, but it's actually dynamical rather than topological.
Mm-hmm. Yeah,
Anyway,
that sounds very interesting. I don't have a good, so it'd be nice to have some example to think about. But
yeah, no, I mean, I found your talk very thought provoking. I was thinking, I wonder whether you could do that. That might be kind of cool for, but you know, anyway. Not really a question, but just sort of.
Yeah. It's more like a project, I think.
Yeah, exactly. But anyway.
Along those same lines, I just wonder whether there's some larger lessons to learn here. You know, you did this nice thing where you stepped back and reminded us why the three-dimensional example is in some ways very analogous to what we do with string world sheets. And I just wonder whether there's a story there where we might sort of go back and revisit some of the things that we were doing and see if there's more things to do. That may already be contained in your conjectures at the end with regards to the constraints from the central charge. But it just seems interesting to me that maybe there's some things we've been doing with world sheets that we should be doing in space.
Right. Yeah. Maybe there can be alternative formulation of world sheet theory that way.
Yeah. And maybe there's some interpretation that.
Yeah. So far there is no holographic description of world sheet gravity theory. So that it might be interesting to see whether this can give us some insight into that.
Yeah. Indeed. Yeah. Any more questions before we go to the break? And I will put a reminder as to how we go to the break shortly.
Let me close
one more question.
There's a question. Go ahead.
Hi, Hiroshi. I'm Juxi. I would like to ask a question on the same topic, on ensemble averaging of rational CFTs. So we observed the same thing for some examples, that the modular sum gives a summation of different CFTs, but we don't know how to interpret the weights of different CFTs, namely the meaning of the distribution. Do you have a physical understanding, or preferably from a gravitational point of view?
No. So these are, you get a very interesting coefficient. And actually, so we got confused because probably you will discuss that in your talk. But for example, you will have to rescale the partition function in order to make sense of this and things like that. And so we don't, I have to confess, except for this positivity issues, we don't have a good understanding of what's going on. So that's why I have been looking forward to your talk. So maybe we can have a more informed
I want to talk about the
after
ensemble averaging, but yeah.
Yeah, thank you.
Yeah, thanks for a very nice talk.
I think I see another question.
Oh, hi, Hiroshi. So regarding the summation of the rational CFT, so the weights are not equal, right?
No.
And
the weights are not equal, and these are rational numbers. Yeah. So that was what Jushi was asking. What the meaning of these numbers? I don't know. Yeah. So the thing is that for continuum case, for Calabi-Yau case, OB4, etc. We are averaging over the modular space generated by marginal perturbations. So in that case, we can use the homological metric, which is a very canonical choice. So if we as a measure, so since there's a homological metric, we can define measure for the averaging. So that seems to be a very reasonable choice, and then it works. For rational CFT, where you have just discrete point, and it's not clear what is the rule that we should use, and that's related to the question Feng asked. Well, what do we mean by summing averaging this over discrete point? And yeah, so somehow there are different weights for different conformal field theory for some reason I don't quite understand.
Okay, thanks. Oh, so another maybe naive question. So maybe I missed that. What is the motivation to consider the double branch cover over the Tango?
Oh yeah. So the motivation was that we are considering orbifold theory, and we are trying to understand the bulk dual of correlation function of twist operator. So if we have twist operator in conformal field theory, your branch cover on the boundary. And the way that the people in the 80s developed to calculate this correlation function, expectation value of product of twist operator, is to consider double cover over these branch points. And then you just calculate partition function there, basically. That gives you correlation function. So what we are doing is the bulk version of this. Namely, in the bulk, if you have twist operator, you have a vortex ending on each of these twist operator. And then it's natural, therefore, to consider the double branch cover over these vortices in the bulk. And you just calculate the Chern-Simon partition function over the universal double branch covering. And then it gives you this answer, which agrees with conformal field theory averaging result. So that gives you that gives you a nice match between the boundary calculation, boundary averaging calculation, and the bulk calculation. Okay. Does that make sense?
I see. Yes.
Thank you.
Okay, thank you.
Hi, Clifford, you're mute.
Thank you. So yes, let's carry on having our discussions, but let's move to the other space. So I'm just going to remind you how to do that. And for those of you who came a little bit late, let me remind you as well to look in the chat box, and you will see a link and a password. It is important that you do it in Chrome, unfortunately. It only takes a few minutes to find Chrome, Google Chrome, and download it to your desktop. It does not work very well using other browsers. You're welcome to try, but it's very buggy. And if you go there, you will find the gather space. Let me just show you what that looks like, where we will gather. And you will be able to wander around that space. I think there's some people who were trying it out earlier. And you'll be able to talk with people and also use the whiteboards and write on them and things like that. For those of you who want to write on the boards, you can even use something like Sidecar to connect your pens, your iPads to your desktops and do it that way. And whatever other equipment you have, there's going to be equivalent ways. So it should work reasonably well.
Yeah. Can I ask you to keep this Zoom session on so that
yes.
if I forget the link, I can come back?
Exactly. The intention is the Zoom link will be on the whole time. And but I'm also going to put these on just some instructions on screen.